So we have already examined bonding in alkanes on example of methane and ethane. Next is bonding in ethene or ethylene. That's an alkene. Alkenes have carbon-carbon double bond. And so valence requirements of carbon of 4 are satisfied by carbon making double bond with another carbon atom and, of course, 2 single bonds with hydrogen. Hydrogen can form only single bonds. So in this case, carbon forms 3 sigma bonds and 1 pi bond, because in a multiple bond, only one bond can be sigma between the 2 nuclei, and the other ones have to be above and below. Those are pi bonds. We'll see that in a minute. So in this case, again, we have promotion in the course of bonding, promotion of electron, but then hybridization is different. Hybridization is sp2, because we need only 3 sigma bonds, and the remaining p orbital remains unhybridized. So 1 s and 2 p orbitals hybridize. Numbers in superscript tell you how many bonds are hybridized, how many orbitals are hybridized. So 1 is understood because if you list it, there is at least one of them. So it would be like S1p2. That's sp2. Shape you can see is same as sp3 hybrid orbital. I shaded them differently just to show you that shading is arbitrary. We can shade these lobes whichever we want, dark and light, any way we want. Arrangement is trigonal planar. So 3 hybrid orbitals are trigonal planar to be as far apart from each other as possible, and unhybridized p orbital is perpendicular to them. It's at 90 degrees to them. And this is view from the top. This is unhybridized orbital. You see white lobe, view from the top. So you can see trigonal planar hybrid orbitals. If we indicate hybrid orbitals as bonds, here in the plane of the drawing, solid line projecting towards your wedge, away from your dash, or view from the top. Angles are 120, of course, trigonal planar. And then in ethene, so hybridization results in formation of sp2 hybrid carbon. 2 of them form a bond where hybrid sp2 orbitals form carbon-carbon sigma bond. Remaining hybrid orbitals form bonds to hydrogen, or hydrogens, 4 hydrogens. And then these 2 unhybridized p orbitals, shown here completely in black. To avoid confusion, I didn't show 2 different lobes, just in black. Overlap side to side to form a molecular p orbital. And p orbital has 2 lobes, one above and one below. And so you can see why second bond has to be, pi orbital. Why it has to be pi. Because sigma already occupied this best region of space, shortest distance between 2 nuclei, internuclear axis. And so pi bond is above and below. And here is another representation showing sigma bonds as lines. So you can see pi is above and below. Bond angles are actually approximately 120, not exactly 120. But on the test, mine and anybody else's, you should always answer 120, because we don't expect you to memorize each individual bond angle. There is nothing special about that. Now, when it comes to bond length and bond strength is inversely related to bond strength, which means the stronger the bond is, the shorter it is. That makes sense because the nuclei are closer together. That means strong bond. Long bond is weak bond. So carbon-carbon bond, because it has 2 electron pairs connecting 2 carbons, is stronger and shorter than sigma bond. So you need to now memorize strength of carbon-carbon double bond or length. It's 1.34 angstroms. Single bond is 154. Now when carbons have different hybridization in each single bond gets a bit shorter. It's 150 in this case. Note that carbon is attached to hydrogen, but it's sp2 hybridized carbon, not sp3. Carbon-hydrogen bond gets shorter, 108 angstrom, instead of 110 for sp3 carbon. All of those you need to know. And when you make this molecule by molecular models, depending on type of the model, double bond may be, we don't distinguish between sigma and pi in models. So 2 double bonds are shown as being identical. 2 bonds, sigma and pi. And so it's either double bond like this, two straight bonds, or what we call banana bonds, bent bonds. In this model set that I ask you to purchase, this is a double bond. Sorry, I'm showing it where I see myself. So this is a double bond. Okay, I will use it next page. Just so that you know if you're already playing with models. And space filling model shows you the shape is kind of flat like a pancake. And then next we have ethyne or acetylene. That's an alkyne. Alkynes are characterized by carbon-carbon triple bond. And so those are linear molecules with carbon-carbon triple bond. So valence requirements of carbon are satisfied by formation of 2 sigma and 2 pi bonds. In multiple bond, only one can be sigma, rest are pi. And so promotion involves promotion of one s and one p orbital to form, promotion of s electron to p orbital, and then hybridization of one s and one p. I'm rushing a little bit. So one s and one p to form hybrid sp orbital. So those are two hybrid sp orbitals, and two p orbitals remain unhybridized. Again, shape is the same as that of sp2 or sp3 hybrid orbital. This is actual shape, and these are stylized shapes. Two hybrid orbitals are linear. They point exactly opposite from each other. That's as far apart as possible. And unhybridized p orbitals are at 90 degrees to each other and two hybrid orbitals. And this is view from the top. Here are hybrid orbitals shown as lines. Unhybridized again shown. Again, view from the top. And kind of view at an angle best shows the bonding. So two sp hybridized carbons bond. I'm again losing picture. I don't know why. I don't know if you're losing it, but I'm going to stop until it comes back. Okay, it's back. So two sp hybrid orbitals overlap to form carbon-carbon sigma bond, and remaining hybrid orbitals form carbon-hydrogen bonds. Unhybridized p or atomic orbitals overlap side to side to form molecular pi bonds, two of them. And so here is Lewis structure showing only sigma bonds, showing sigma bonds as lines and pi orbitals. Now there would appear to have that we have two pi orbitals, kind of distinct pi orbitals at 90 degrees to each other, but actually really triple bond is fundamentally different from double bond, where you really have that side-to-side overlap. In a triple bond, actually, because pi orbitals penetrate each other, this is really slow. Yeah. This is view kind of edge on. Looking along the carbon, we don't see carbon-carbon bond, and we remove the hydrogen. So this is what you would think is triple bond. Two pi orbitals at 90 degrees to each other. Of course, the other carbon is right at the back. But actually, these orbitals penetrate each other and form a tube of density. So two pi bonds actually surround the sigma bond and so form a tube of electron density. And here is another representation. You have a nucleus, and the other nucleus is right behind on the other side. Sigma orbital that connects the two nuclei, and then two pi orbitals around. So they are not like this, distinct two pi orbitals. They are more like a tube of electron density that surrounds the sigma bond. And only if one of them reacts, then the other one appears 90 degrees to it. But unless they react, there is a tube of electron density. And that means that the reagent can approach at any angle and react. And that makes triple bond much more reactive than double bond. And here is how we represent triple bond. Either three identical bonds or three banana bonds. And you can see space filling model shows actual shape like a sausage. Of course, triple bond has angle of 180, and it's not approximately, it's always exactly 180. Bond length is 120, even stronger and shorter than double. And carbon-hydrogen bond is 106 angstroms, even shorter. So carbon-hydrogen bonds have different length depending on hybridization of carbon atom. And sp hybridized carbon atom exhibits shortest bond to hydrogen, sp2 intermediate, sp3 the longest. That could be an exam question. So make sure that you know those bond lengths, shorter, longer length, and so on. It could be exam question where you pick out what is the particular length, which one is the shortest, which one is the longest, shortest carbon-carbon, longest carbon-carbon, longest carbon-hydrogen, shortest carbon-hydrogen, or which one has a length of like that, particular length and so on. Now you have already seen that hybrid orbitals have the same shape, and they are different, sp, sp2, sp3. So what makes them different? It's the size. So sp has the smallest size because it's most like s orbital. It has 50% s character, one s and one p. So it's smallest in size. And sp3 is the largest in size because it has least s character. S orbital, of course, is smaller than p. And so it's the size that makes a difference. And that explains also the length of carbon-hydrogen bond. Because carbon-hydrogen, hydrogen is at the other end. If it's sp hybridized carbon, it's the smallest hybrid orbital, so it's the shortest and strongest bond. sp3, largest orbital, longest bond, because hydrogen is at the other end. And here are bond lengths. There is an error. If you have print version of my book, which is no longer available, there is an error here. So let me see if I think that this is correct. I think that this error has been corrected here because this is R1, this is revision 1. So I think that the error has been corrected. Yeah, these all look reasonable. So these are correct lengths. And then reaction intermediates, another important topic. Reaction intermediates are short-lived species, but they do have definite lifetime. So reaction intermediates are charged species or species with unpaired electron. So hydrogen ion is actually proton, hydrogen that has lost its electron. Hydride ion is hydrogen atom that has gained an electron. So it has electron pair and negative charge. Of course, hydrogen ion, positive charge. Hydrogen radical is identical to hydrogen atom and has one unpaired electron. So those are hydrogen intermediates. Carbon intermediates are more complex, and you need to know them in detail. They are used or encountered throughout this course. So they are carbocation, carbanion, carbon radical, and carbene. We can start with methane, and then in a hypothetical process from methane generate all these species. If we remove hydrogen, if hydrogen leaves and takes electron pair with it, carbon is left with an empty orbital here and positive charge. That's methyl cation. If hydrogen leaves as a proton and leaves electron pair on carbon, then carbon has a free electron pair and negative charge. That's anion, methyl anion. That's called heterolytic bond breaking, where one atom retains electron pair, the other one leaves without it. Homolytic bond breaking is even breaking of the bond. So each atom gets one electron. In homolytic carbon-hydrogen bond, we end up with methyl radical, carbon radical. And if two bonds are broken homolytically, then we end up with carbene. So radical and carbene, because of the homolytic bond breaking, don't have any charges. So what is the bonding? Well, in case of methyl cation or any carbocation, carbon has empty p orbital, geometry is trigonal planar, and hybridization is sp2. You need to know this for the exam. This is often on the test. So carbocation, so you need to know bonding in each of these species. Carbocation sp2 hybridized, trigonal planar, and empty p orbital. The same is actually for free radical. Radical is also sp2 hybridized, trigonal planar, and unpaired electron is in unhybridized p orbital. Methyl anion is sp3 hybridized. Now geometry is actually pyramidal. sp3 hybridized means that electron cloud is tetrahedral, but electrons don't count in geometry because we can't see them. So we can only see carbon and 3 hydrogens in the trigonal pyramid. So geometry is trigonal pyramidal and sp3 hybridization. So you need to know hybridization, geometry, what they look like. And then carbene is the most complex, CH2. It's called methylene. There are two different carbenes, singlet and triplet. In singlet carbene, electrons are paired up. So they are paired up in hybrid sp2 orbital. There is unhybridized empty p orbital and two carbon-hydrogen bonds. Geometry is, of course, bent because you only see this bent shape, you don't see electrons. In triplet carbene, hybridization is sp3, and each hybrid orbital has one electron. And again, geometry is bent. Names singlet and triplet come from spectroscopy. Spectroscopy is covered in Organic 2. So at this point, there is no way to explain that to you because we didn't cover spectroscopy. But simply, singlet gives one signal in the spectrum, while triplet gives 3 signals. And now we should examine bonding in molecules that are inorganic molecules that are relevant to organic chemistry. First, ammonia and ammonium ion. Ammonia is NH3, so hydride of nitrogen. So this is electronic configuration of nitrogen. There is no promotion in the course of bonding because promotion of s to p orbital, electron from s to p orbital, would not increase number of unpaired electrons. And so there is nothing to be gained. Because if electron were to be promoted from s to p orbital, it would pair up with one of these. And so there's nothing to be gained. So just hybridization occurs to form 4 orbitals of equal energy and identical properties. So 4 hybrid sp3 orbitals, but only 3 of them can bond. And so 3 bonds to hydrogen are formed. This electron pair remains on nitrogen as free electron pair. So geometry is trigonal pyramidal. You can see it from the model. We don't see electron pair. And this is space filling. Now, ammonium ion has hydrogen bonded to electron pair, proton bonded to electron pair. So it has a charge of +1. It's ammonium ion or ammonium cation. It's isoelectronic with methane. It means it has same number and same electronic configuration as methane, as CH4. And so it looks just like methane. That's why we identify species that are isoelectronic, because they resemble each other. So it's tetrahedral, just like methane, and it looks just like methane. The only difference is positive charge. Another important molecule is water, hydride of oxygen. So oxygen, this is electronic configuration of oxygen, 1s2, 2s2, 2p4. Again, only hybridization occurs. There is no promotion because it would not increase number of unpaired electrons. And of course, this is formula of water, Lewis structure. And you can see a molecule of water has bent shape. 2 free electrons, so two free electron pairs. Now, how do you know hybridization of atom in advance? For some atoms, you cannot figure that out. Let's say sulfur. We have to tell you that. But for carbon, nitrogen, or oxygen, hybridization is sp3 minus number of pi bonds and pi orbitals. So that's how you know that water is going to be, oxygen and water will be sp3 hybridized. No pi bonds, no p orbitals. Same nitrogen, you know it's sp3. Triplet carbene, sp3 because there are no pi orbitals. So no p orbitals. One p orbital, it's sp3 minus 1, sp2. There's one. No p orbitals, sp3. One p orbital, sp2, sp2. And here, 2 pi bonds, so it's going to be sp. sp3 minus 2, so sp. And so here are some more examples. Sometimes it's a little bit difficult to figure out whether there is atomic p orbital on an atom. But pi bond, you know easily, because that's multiple bond. Second bond is 1 pi bond. And second and third bonds are 2 pi bonds. And note that you could have 2 double bonds on the same atom. One of each is pi bond, that's total of 2 pi bonds. So this is sp hybridized. So practice this so that you know for the exam you can figure out what is hybridization. Again, that also could be an exam question. Now there are 4 chapters. There's going to be a limited number of questions from chapter 1, but I'm telling you most likely questions. We can figure out geometry of molecules by using VSEPR method, valence shell electron pair repulsion model. That's one of the models that we teach in general chemistry, and it's shown here. It's also explained in the video. I'm pretty certain there's video on YouTube on that. I remember making it. It wasn't easy, that's why I remember making it. The other is from hybridization. So those are 2 methods. One is hybridization. To memorize, sp2 is trigonal planar, sp3 tetrahedral, dsp3 trigonal bipyramidal. That's less used in organic chemistry. Or following VSEPR method. You can go through VSEPR method following it here. In organic chemistry, we typically more commonly use hybridization, while in inorganic, VSEPR method is more commonly used. That's because VSEPR is a bit more general. Now note that for a larger molecule like this, we cannot tell about overall geometry of the molecule. You can tell that this carbon is tetrahedral and this CN group is linear, or this carbon has linear geometry. But overall molecule doesn't really have any particular geometry. We can only talk about segments of the molecule. And then when it comes to bonding in hydrogen halides, we don't have any geometry. Hydrogen halides, those are group 17 elements, bonding of hydrogen with fluorine, chlorine, bromine, or iodine. There is no geometry because there is only a single bond. What we are looking at is bond length. And bond length increases with increasing size of the atom. So fluorine, chlorine, bromine, iodine. And that means that bond strength decreases. So hydrogen-fluorine bond is the shortest and strongest, and then it becomes progressively longer and weaker. That's because of the orbital that is used, that halogen uses to bond with hydrogen. Fluorine uses 2p orbital. That's small, short orbital, and matches very well with hydrogen orbital. That results in formation of short and strong bond. Chlorine uses 3p orbital, and 3p orbital is much longer, and you see how these lobes are cut. So this lobe is cut by spherical nodes to 2 different lobes, and this one is not bonding. It's not in the same. It's not shaded the same way, not same phase as hydrogen. That results in longer and weaker bond. And then bromine uses 4p orbital, which is even longer and weaker, and iodine 5p, longest and weakest bond. You need to know this. This is important because it will be important later when we also cover carbon, bonding of carbon, and the same principles will apply. And finally, we were talking about polar covalent bonds. Some molecules overall are polar if they exhibit dipole moment. But to exhibit dipole moment, 2 things are needed. First, molecule must contain polar bonds. So if all the bonds are non-polar, it's not going to be polar. But if bonds are polar, they also must have such a geometry that individual dipoles don't cancel out. So what we do is we look at vector sum. Vector, each polar bond can be described mathematically as a vector. Vector is quantity that has direction, goes from positive to negative end of the dipole, and magnitude. What is the size of the charge separation? The larger charge separation, the greater the magnitude. And unit for dipole moment is d, or debye. So direction of the vector is always towards the more electronegative element. And you would know that from table of electronegativities, or knowing that electronegativity is periodic property. So these are for some bonds individual vectors, but they must not cancel out. So when they will cancel out, if species are identical and you have symmetrical molecule. So if molecule is tetrahedral, if all four substituents are identical, then there is no dipole moment, because even though individual bonds are polar, it doesn't matter which way they are polarized, away from carbon or towards carbon. The individual dipole moments cancel out, and overall molecule is nonpolar. Or linear molecule, two bonds point in opposite directions, again nonpolar. And this shows you common examples of nonpolar molecules. So for linear, if this is central molecule A, if outer molecules are identical, then it's nonpolar. Trigonal planar, again, if these three are identical, nonpolar. Tetrahedral, nonpolar if all four are identical. Trigonal bipyramidal, again, nonpolar if all five are identical. If only one of them is different, molecule is polar. Different, that could mean free electron pair. So this is the tetrahedral shape of the electron cloud, but one of them is electron pair. It's very strong dipole moment because electrons are negatively charged. Very strong dipole from positive nucleus to electron pair. And of course, with two electron pairs, even greater dipole moment. And here we have an example of the tetrahedral molecule with one different atom. And again, molecule is polar. So that's how we recognize polar molecules from non-polar. And it's very important for study of chapter 3, which we'll cover the next day. So I planned to cover chapter 2 today, but I will leave it for the next day. It's much better because first, I'm very tired, and also probably you are also very tired by just by listening to me for this long. So this is everything I planned to cover. So let me first just check if there are any